This is a video for AQA Further Pure Mathematics. In this video we're looking at complex numbers section 1.1, solving quadratic equations with no real roots. Well, first of all, just a reminder about solving quadratic equations of the type that you already have met. For example, if we look at this equation, x squared minus 5x plus 6, then I think quite quickly you'll see that this can be factorized. And so if we look at the factors for that, we see they are x minus 3 and x minus 2. And therefore x is equal to 3 or x is equal to 2. Now, if you weren't able to see the factors there, we could have used a quadratic formula. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Or indeed we could have completed the square. So any of these methods would have worked, but in this particular case factorization is probably the easiest. Now, all the equations that you've met so far have had either two real roots such as this one, or perhaps you would have met ones which have a repeated root, for example x minus 5 all squared equal to 0. And in that case we've got a single root, x equal to 5, which we consider as being a repeated root. Sometimes we have equations which produce irrational numbers as their solutions. So as an example of that on the next slide. In this case we could again use the quadratic equation. However, I'm going to do this by completing the square. So if we do that, we get x minus 2 all squared, and then remember that you're going to subtract from that the value of 2 squared, so we have then minus 4 minus 13 is equal to 0. So therefore x minus 2 all squared minus 17 is equal to 0, and so x minus 2 all squared is equal to 17, and taking the square root, x minus 2 is equal to plus or minus the square root of 17, and then we can add 2 to give us our two solutions. X is equal to 2 plus or minus the square root of 17. So here we've got then two roots which are irrational. If we calculate the discriminant, in this case b squared minus 4ac, we get the value of 68, which is greater than 0. So that tells us that we can actually find our two roots as being real numbers. Let's look at a different equation, this time where we've got plus 13 rather than minus 13. So if we attempt to complete the square here, again we get x minus 2 all squared, and then minus 4, but plus 13 equal to 0, and therefore x minus 2 all squared plus 9 is equal to 0. This time we need to subtract 9 from both sides, so x minus 2 all squared is equal to negative 9, and we try to take the square root, so that x minus 2 is plus or minus the square root of negative 9. Now we know that the square root of negative 9 is not a real number. However, we can write it as the square root of 9 multiplied by the square root of negative 1, just using the rules of roots. And so therefore we have that this is plus or minus 3 times the square root of minus 1. So that x is equal to 2 plus or minus 3 times the square root of minus 1. Now these are not real numbers. However, if we allow the square root of minus 1 to exist by introducing a new type of number called imaginary numbers, then which we represent by I, then we can say that we have got two roots which are 2 plus or minus 3 times I. So we've got x equals 2 plus 3i, or x equals 2 minus 3i. So by introducing this new type of number, we have got roots for these new types of quadratic equations. Now they're not real roots, these are what are called complex roots. So the numbers 2 plus 3i and 2 minus 3i are referred to as complex numbers, where 2 is the real part of the number and the imaginary part of the number is 3. Notice that that imaginary part is simply the coefficient 3 and it's not 3i. The imaginary part of the number 3, the real part of the number 2. So that's the end of this video. In the next one, section 1.2, we'll be looking at these complex numbers in more detail, and in particular adding and subtracting complex numbers.